The Celtic Engineer is a weekly newsletter produced by Celtic Engineering Solutions, LLC. We hope you enjoy it. If you have any suggestions for topics or would like to give feedback, please subscribe on our website. Batteries. Who's got your joules? So, I am making this battery-powered device, and all I want to know is how many batteries do I need to make it last forever? As engineers, we take some things for granted. Specifically, we think that everyone understands the world of electronics the same way we do. So when we talk about system voltage, battery capacity, and usable life, we can often get the response, right, so how many batteries do I need? It's a fair question, but not an easy one to answer, especially when you have a microcontroller, MCU, on board. The reason is because an MCU does not use the same amount, a constant amount of energy, all the time. We might as well start with the idea that energy and power are not the same thing. Energy is the capacity to do work. Power is the rate at which work is being done. Energy is expressed in the units of joules or watt-hours. 1 kilowatt-hour, the units of energy the power company bill you for each month, is equal to 1 million joules. Mechanically speaking, a joule is the amount of energy used when you apply a force of 1 Newton through a distance of 1 meter. Electrically, it is when 1 amp is passed through a resistance of 1 ohm for 1 second. Power is the rate of energy consumption. It has the units of joules per second or watts. Watts are found by multiplying the voltage and the current in a DC electrical circuit. That energy can be consumed at different rates. This should be pretty clear. If not, you will want to go back and listen to that last section again, because here is where things get messy. A typical AA battery has a capacity of 2850 milliamp hours. So quick quiz, is an amp hour a unit of energy or power? It's actually a trick question. The answer is neither. It is a unit of charge. Basically, the battery companies are telling you how many electrons they have put in the battery for you to use. It really does not help you answer the question of how many batteries you need. The idea behind the amp hour is that it tells you how many amps an ideal battery can deliver for a certain amount of time. So a 2850 milliamp hour battery can deliver 2850 milliamps, 2.85 amps, for 1 hour. Or it can deliver 1425 milliamps for 2 hours, or 28.5 milliamps for 100 hours. The system voltage is the voltage at which the device operates. There may be several system voltages, but to keep this simple, let's imagine a battery-powered device that has a system voltage of 3 volts. 3 volts is nice because many MCUs will work with that voltage. The input voltage is usually higher than the system voltage. To compensate for this, we use regulators. A regulator takes in 1 voltage and puts out another. A very simple type of regulator is called the linear regulator. It is frequently used in battery-powered devices. It will take in a voltage of 4.5, 6, 7.5, or 9 and put out a system voltage. In our case, that is 3 volt. You might think I chose a strange assortment of voltages, but they are just the nominal voltage of new batteries, either 3, 4, 5, or 6 in a row. You might wonder why not just use 2 batteries to get 3 volts and be done with it. Notice I said ideal battery above? Real batteries cannot perform that way. They have a maximum current that can safely be drawn. In fact, a real battery has a discharge curve. So, we can't use 2 AA batteries to get 3 volts, because soon after we start drawing current, the voltage begins to drop. We might use 3 AA to start with 4.5 volts. The regulator keeps the voltage constant to the E system at 3V, even while the battery voltage falls from 4.5 volts. The regulator does this until we bump into a parameter known as the dropout voltage. Every regulator has a dropout voltage. They range between 0.1 volts and 0.5 volts, typically, for most regulators. This is the difference between the input and the output voltages that the regulator needs to do its job. Once the dropout voltage is hit, as the input voltage continues to drop, the output voltage no longer stays constant, but will also drop, while still maintaining that same voltage across the device, say 0.1 volts for a good regulator. When your batteries are 3.1 volts, your system voltage will begin to fall. How far it can fall before the system stops working is dependent on what type of chips you are using. A 2.75 volt is not unreasonable. That will happen in our fictitious device when the batteries are at 2.85 volts, 0.1 volt across the regulator. Our device will stop working when the battery voltage gets to 2.85 volts, not when it is completely depleted. For that reason, and because battery voltage is continually dropping, it is really hard to decide how many batteries you need. When you stack batteries in series, the capacity of the string is the same as the individual battery, 2,850 milliamp hours for AA's, and you add the voltage. But when we put batteries in parallel, the capacity adds and the voltage stays the same. So 2 strings of 3 batteries is still 4.5 volts, but the capacity is now 5,700 milliamp hours. What is the typical capacity of different sizes of batteries? A AAA is 1,150 milliamp hours, a AA is 2,850 milliamp hours, a C battery is 8,000 milliamp hours, and a D battery is 18,000 milliamp hours. It is easy to see that 3 C-size batteries are a much better choice than 6 AA batteries arranged in 2 strings of 3 if you can handle the increased size. One side note is that when you put strings of batteries in parallel, you don't just connect them together. If you do, and one battery discharges at a rate slightly different than the others, you can wind up in the situation where one string is charging the other string. While undesirable with rechargeable batteries, when this happens with non-rechargeable batteries, an unsafe condition exists. To fix this, we put a diode in series with each battery string. Current flows out of the string but cannot flow back into the other string. And of course, there is a voltage drop across the diode. 100 milliamps times the voltage drop across the diode is waste heat. At low currents, typical battery-operated devices, and proper diode selection, you can see a forward voltage drop of a few hundred millivolts. At 0.1 amps, that's tens of milliwatts, not too bad. So how do we figure out how many batteries we need? Will you hate me if I say an educated guess? We can spend lots of time modeling the current consumption because real devices are not going to draw a constant current. We can calculate the amount of energy used over the life of a set of batteries and drop out a number that says it should last this long. Reality is, your mile may vary. Time is best used when we make a good, educated guess. Build a prototype and try it out in something like a real-life use case. Then you can go back and decide which arrangement of batteries will best work for your device. That is why prototyping is very important. I had a professor in school who swore that the circuit never lies. It might deceive you, but it never lies. We hope you've enjoyed this Celtic Engineering Solutions moment. Remember, folks, when it comes to batteries, always stay positive and grounded. Because if you're feeling drained, it's time to recharge. But if you're overcharged, well, that can be quite a shock. I'm Sean O'Leary, licensed PE out of Murray, Utah. This podcast is sponsored by Celtic Engineering Solutions, LLC, a design engineering firm based out of Murray, Utah, which can be found on the web at Celtic Engineering Solutions.